Welcome back to our course in quantum computing and quantum machine learning. The topic this week, after we've gone through a reminder from last week, is to continue our discussion of entanglement. We will also bring up a technicality which is very much used in order to define what we call pure states versus mixed states. And this is called the Schmidt decomposition, which is essentially based on the singular value decomposition, which is a famous algorithm in linear algebra. Then we are going to bring up some of these elements about the entropy as a measure of entanglement. So entanglement is a quantity which cannot be observed. It's not an observable, but we can, through other quantities like the entropy, we can define a measure of how a state is entangled. Now, keep in mind that there are many ways to define this entropy or measures of entanglement. We will stay with what has been a common way of doing that, which is called the von Neumann entropy, which is the quantum mechanical equivalent of the classical Shannon information entropy. And last week, we went through the derivation of the von Neumann entropy using the density matrix. We will remind you quickly of some of these things. And then we will move over to this simple Hamiltonian, which is a 2-qubit system, where we then will calculate the trace of the density matrix for a specific subsystem. This is parallel to what you would call for the marginal distribution in statistics. And we are coming back to these. But then the second half of the lecture today is going to be dedicated to an introduction to quantum mechanical gates. And these gates are the basic building stones for the projects which we will work on till the Easter break. And we will also introduce a software which is called Qiskit, which is a library which has been developed by IBM, which allows us to operate on these gates. Keep in mind also that if you go back to the GitHub address of the course, there is a detailed plan for the different weeks, and you will find again the videos of the lectures, the whiteboard notes, and the reading recommendations. So like for this specific week, you have received chapter 2 and chapter 3 of Robert Hunt's book, which is very relevant for the exercises which we will deal with next week. So next week, if you scroll down to the bottom of the Jupyter notebook for this week, you will find a set of exercises where we are going to play around with different states and perform operations of these on these states. And the states which we will focus on are the so-called Bell states, which we introduced last week. I'm going to remind you of the Bell states as well today. So there will be elements of repetition from last week, but we would need that one in order to link that with the exercises next week. The first project, as announced through the email I sent yesterday, is going to be available during this weekend so that we can get started with the hands-on exercises when we start next week. So next week, we will not have a regular lecture, but we will actually have a hands-on session where we try to get started with the project and look at some of these exercises, which include the setup of gates and thereby quantum mechanical circuits. Okay, any questions so far? Feel free to put questions in the chat, or if you wish to unmute yourself, please feel free to do that. If there are no questions, I'm going to quickly remind you of some of the things which we discussed last week. So the density matrix plays a very important role, as we saw last week when we defined this quantity, which is called the von Neumann entropy, which is used as a measure for entanglement. So let me quickly remind you of some of these technicalities. We did that last week as well, but sometimes it's useful. So a given operator has a spectral decomposition, and this is the way we actually decompose the density matrix for a specific state. And we're assuming that there is an orthogonal and normalized basis I, which are eigenvectors of A of this operator, and this operator has eigenvalues lambda I. And this is the spectral decomposition which we derived in the second week. The trace of a product of matrices are quantities which I just wanted to remind you of. And we also have shown that this trace can be rewritten out as actually this expectation value from the state psi of this operator A. And then the density matrix is a quantity which is now written out in terms of a probability. This is the probability of the density matrix. And these are the states, the orthogonal basis states, which we use to define the density matrix. And this density matrix is a quantity which is invariant on the unitary transformation. That is very important. The density matrix is normalized to 1 if we calculate the trace of the density matrix. So this is another important property which also is important when we are looking at the invariance on the unitary transformations. So this matrix is actually, as I said, it's invariant. So if you look at the trace here, if you look at the cyclic changes, you can always rewrite the last one since U is a unitary matrix in terms of U times U and then the Hermitian conjugate. Now, if we now just spool back in time a little bit and look at the states which we had last week. So we introduced this famous Bell states, and the famous Bell states are states which also constitute an orthogonal basis, but they are given as a tensor product of 2 qubit states. So we can now think of a system A and a system B. And the basis in these two systems is now given by this vector here, 1, 0, which could now be qubit 0, and the other one is qubit 1, which is 0, 1 here. And as we have said many, many times, these subsystems could represent single particle states, or they could actually be the representatives of a composite many particle system with a given symmetry for the specific states. So what we did then was to introduce a computational basis, and that computational basis for 2 qubits is then given by the tensor product of the individual qubits in system A and system B. And it's pretty common when you've gone through this algebra here to rewrite these states in a shorter notation. So 0, 0, that means that you have qubit 0 in system A and qubit 0 in system B. And often you would rewrite this in a more compact notation with just labeling this as state 0. This could be state 1, etc. Now, the Bell states are then another set of states. And what we said last time is that these states are states which we call entangled. And we call them entangled because these states cannot be separated into single products of, let's say, states 0, 0 times another state. So it's actually a superposition of 2 states here. And these states are then given in terms of these definitions, which we presented last week. And the states, as you can easily see, they form an orthogonal basis. So these were the 2 states, the 2 first ones, and then we had the 2 other states. And it's an easy exercise to show that these states are orthogonal. Now, the measurements, which we discussed also last week, so I wanted to remind you of that. When we measure, and this is one of the interesting properties of these specific states, when you measure one of the qubits of these, any of these Bell states, what that gives you automatically is the state of the second qubit. So what we did then, just to remind you what we did last week, was to look at a projection of the qubit in a specific subsystem. So that is given, this projection is given by the projection operator for qubit 0 in system A, and then it's a tensor product with the identity matrix for system B, because we're not doing anything with the identity matrix in system, with system B. So we want to project out the specific state in the system A. And when we take the tensor product of these two matrices, then we end up with this 4x4 matrix. And similarly, we had the projection operator for qubit 1 in system A, since this is a system where the two subsystems have only two possibilities, either qubit 0 in system A and qubit 1 in system A. And this is the new matrix which we end up with when we perform this projection. And when we then look at the probability of a specific outcome, then we will take this specific state which we are looking at. So this could be any of the Bell states. And then we simply trace out or project out the qubit in system A. So this will be qubit 0. And what happens then is that we get a probability of 1/2, which is pretty easy to see. And similarly, we can have a qubit 1, which has the same probability. And that follows simply from the Bell states because we have a factor of 1 over square root of 2. After the measurement, the system is in a new state. So this definition of the state after the measurement is something which we defined earlier this semester. And the post-measurement state is now a state which has collapsed to the state 0, 0. So that means we did a measurement on state 0 of the subsystem A, and then we know exactly that the system B is also in qubit 0. And similarly, if we make a measurement on 1, we know what the other system is. So you see from these equations that the state of the second qubit is determined even though the measurement has only taken place locally on system A. So you could think of these two systems as two well-separated systems where you now operate with, suppose, a laser on system A. And that means that when you then perform a measurement on system A, you know exactly what system B is in. If you then consider a state like this one, that is what we normally call a pure product state of the single qubits, or what we might call the single particle states. And we normally call such a state for what we would normally label as a pure product state or just a plain product states. So quantum states that cannot be written as a mixture of other states, they are normally called pure quantum states or just plain product states, while all other states are normally called mixed quantum states. So this is the way we would define an entangled system. And if we look back at these Bell states, you see now that these states are states which we cannot write out as a product of two specific states. So we say that these are linear superpositions of two specific states, and we normally call this for entangled states. So just keep in mind these definitions. Now, there's another thing here, which is interesting for us, not only because we are going to run calculations with them later, especially next week. We are going to look at measurements which we can make on these states. We are going to set up gates and circuits which can be operated on this, which can operate on these states. I see that there is a question here from Louis here. So let's pause a little bit.
Yes, teacher. I have one question. Can you repeat or explain a little more the difference between pure and mixed state and the relation with entanglement?
So if you look at the state which you have here, this example here, this is normally what we call a product state. So that means that your state is just a product of two specific states. And that means that you can easily then project out either state A is the 0 qubit or the 0 qubit in state B. So this is just the way you define a product state. So let me show you that in another way, because this becomes a little bit important when we are looking at further quantities like the probabilities and the density matrices and the discussions of entanglement. So if you think of a system which has a Hamiltonian which just contains single particle operators, you could now assume that you can make you have an operator in one dimension which acts on a state alpha of x, and this gives us an eigenvalue psi of alpha of x. So you can think of these states as single particle states. So what I could...
Ja, det er det ventet. Det er ganske fett. Jeg er en geek som faen, ok? Du skal spille 4-5. 4-5, ja? Er det brettspill, liksom? Er det sånn som Dungeons and Dragons, hvor man må sette seg ned, og det tar flere uker å egentlig fullføre et spill? Er det sånn typ? Nei, det er som...
I'm going to mute this guy here. So we had somebody who had the microphone on here. Okay, sorry for that. So I muted that person. Let's now suppose that we want to construct a system which now contains two particles. So H0 is an one-body operator. Now what we could make now is an ansatz for the state for two particles, which now contains particle 1, and in principle this should be always written as a tensor product of particle 2 here. What we are assuming then is that there is no interaction, and it's possible then to show that the state psi of x1 and x2 is an eigenstate of a Hamiltonian now, H0, which now contains the two single particle states. So an operator which now acts on the different single particle states. So if I take H0 and act on this operator x1, x2, this is now given by some eigenvalue. Let's call this eigenvalue 0 of psi x1, x2, if we don't have an interacting system. So a product state is defined like this. This is an ansatz for the state of two particles. And since the Hamiltonian of the system doesn't contain any interaction, it's actually possible to show then that this product state is an eigenstate of the non-interacting system. This is something which we discussed last week in connection with the type of Hamiltonian which we were setting up. Now, this is an example of a product state. You should think of this in terms of the way we deal with probabilities as well. So you can think of a probability for two events, two stochastic events, x1 and x2, if these are independent and identically distributed. So this is normally called in statistics IID, independent variables, and identically distributed. Then we can write this out as a, so we should write this as an uppercase P. These other P's are lowercase P's. And this is stochastic event 1 and stochastic event 2. So that, in that specific case, we have probabilities which are just the products of the individual probabilities. This is a very powerful statement which is used widely in statistics. And normally we often assume that events are independent and identically distributed. If you think quantum mechanically, what that means, if we want to make a comparison between this and this, we know that quantum mechanically, the wave function squared is interpreted as a probability. So that means that if we have a non-interacting quantum mechanical system, then the probability of finding the system in position x1 and x2 is simply given by the squared product of these two quantities. So that defines a product state. For those of you who have taken a course in many-body physics, you know that if you have a non-interacting system of bosons, then the system then would also be given by a product of the single particle states, except that you have to obey a specific symmetry. So for a boson, the wave function has to be symmetric under the interchange of two particles. And if you're dealing with fermions, For fermions, the wave function will also be a product state, but then we have to bake in the anti-symmetry. And this is normally baked in by setting up what is normally called a determinant. So this defines a product state. Now, if you have a mixture of two states, so if you think of a fermionic system, and you have a system which now has to have a wave function which is anti-symmetric, then the simplest example of an entangled state is an ansatz for the fermionic state for two particles, so which then will be given by an x1, and then we have the product of these two guys, but then we have minus in order to obey the anti-symmetry, and particle 1 and particle 2 change place. This is an example which you have seen in many textbooks of an entangled state, because this cannot be separated out as a product of two single particle states. Does that help when we talk about pure states or product states?
Yes, thank you.
Okay, so if we then look at these Bell states are then states which are so-called entangled, and we cannot write them out as product states. And if the state here, as we said here, is just a so-called mixed state, and we cannot determine when we look at it, we cannot determine whether system A is in state 0 or 1. So because it's given by a superposition of two specific states. However, and this is something which often is confusing in the beginning, we also call this a pure state. So make a distinction now between a pure product state or just simply a product state, which just contains a tensor product of these states, and what we will label as a pure state. Now, a pure state is a state which is known in the beginning. So we know that the system is in the state phi plus. And in the literature, this is normally called a pure state. And we are going to look at these definitions in connection with the discussions of entanglement. So normally we say that this state is entangled, and it yields a definition of entangled states. A pure bipartite state, like with the one we had here, is entangled if it cannot be written out as a simple product state for any choice of the states which we have. There are states, this state is actually called a Dicke state, which is a maximal entangled state, where all the states here have an equal probability. And the Bell states are an example. One of the Bell states is actually an example of a Dicke state when we have just two qubits. And the other thing which is going to be important for us a little bit later is actually the density matrix. So the density matrix is then normally given as the tensor product of the density matrices for the different subsystems multiplied with the probability for being in that specific state. Now, one thing which I wanted to bring up, and which I'm going to do by slides here, so I hope you can forgive me for that, is the Schmidt decomposition. That is a technicality which is going to be pretty useful a little bit later when we are going also to discuss entanglement. So just view this as a plain technicality, which we will bring back a little bit later here. So this Schmidt decomposition is based on a famous theorem in linear algebra, which is called the singular value decomposition. So the Schmidt decomposition allows us to define a so-called pure state in a bipartite, I'm probably not pronouncing this correctly, a bipartite, I have to look it up, actually. Sorry for that. And a Hilbert space, which is now composed of two systems. So this is what the Schmidt decomposition says, and we are going to look at the proof of this statement, which you see here. So what it says then is that these amplitudes are real and positive, and their squared values sum up to 1. These states they form an orthonormal basis for systems A and B, respectively. And the amplitudes are what's normally called a Schmidt coefficient. And the rank D is equal to the number of Schmidt coefficients and is smaller or equal to the minimum dimensionality of subsystem or system A and system B. So if you think of the Bell states, the way we have written them, if you look at them now, is actually an example of such a Schmidt decomposition. So if you look at the Bell state, let's go back again. If you look at this specific state here, it has a factor of 1 over square root of 2. If I'm going to square these quantities and sum them up, that's going to give me a factor of 1. So the Bell state is an example of such a Schmidt decomposition. Thanks. There is somebody who helped me with the pronunciation of that word here. Sometimes there are words which you've heard, and then you don't remember the right way of saying it. I hope you can excuse me for that. So the proof for this decomposition theorem is based on a famous theorem in linear algebra. This is actually, and this is a personal statement, it is my favorite algorithm, the singular value decomposition. Because you have, just to say a little bit about the singular value decomposition, the singular value decomposition tells you that you can always decompose a matrix which does not need to be a square matrix. You can always decompose it, even if the matrix gives you a determinant which is 0, or it has eigenvalue 0. It can be decomposed in a orthogonal matrix U times a matrix which is diagonal and contains the so-called singular values times another orthogonal matrix V, or unitary matrices. So the basic idea now is that you can construct a product state, which is also a pure state. So when I say a pure state, keep in mind that we know exactly what the state looks like when we start. So the coefficients which you have here, theCij's, they are the overlap coefficients which belong to a matrix C. So what we have done here is simply to look at a product state and then have a coefficient here which tells us how these mix in order to make up the final state psi. The way this is done then is then to assume that the dimensionalities of these two subsystems are the same, and you can always rewrite the matrix C in terms of a C. So this C is a matrix. So these are the components of a unitary transformation. And you can always rewrite that. They don't need to be a unitary transformation, by the way. But in our case, we are mainly going to deal with unitary transformations. So the matrix C can always be decomposed in an orthogonal matrix U and an orthogonal matrix V. And if we now assume that the matrices have the same, these two subsystems have the same dimensionalities, then we are dealing with square matrices. So, and sigma here contains the so-called singular values, and there are different ways of organizing them. You can organize them in an ascending way, so that the singular values start with the lowest one and keep increasing, or you start with the highest one and keep decreasing. That means that we are going to write this matrix as a singular decomposed matrix. The SVD then, that means that we can rewrite those coefficients which we have here in terms of the singular value decomposition. And the columns of that matrix U give an orthogonal set of vectors. The columns of the matrix V are also forming an orthogonal basis. So we can actually rewrite this coefficient Cij in terms of this sum here, where we have the matrix elements, we have the singular values, and then the matrix elements of the other orthogonal matrix. If we now insert these, into this so-called pure state. So keep in mind now that when we use the definition of pure state, this is not what we labeled earlier as a product state, but this is a pure state where we know exactly what the system, which state the system is in when we start manipulating this system. So it means then that we can rewrite this state like this. And if we now look at these summations here, we can now rewrite the summations. So the ij here is now simply being multiplied with the coefficients, which we have from a singular value decomposed matrix. And that means that I can rewrite them like this, where now these I and j's, they are now the vectors of this this singular value decomposition. So if you look at this now, what I have is that these are orthogonal vectors, these are orthogonal vectors, and then I'm simply left with this coefficient here multiplied with two orthogonal vectors and normalized vectors if we want to normalize them. So this is just a proof that we can decompose this general state which we had here, the state which you see here, in terms of this specific decomposition, which is now called a Schmidt decomposition. We are coming back to what this actually means. So when we have this Schmidt decomposition of a given state, we can immediately say whether it is entangled or not. If that state is entangled, then the Schmidt decomposition has more than one term. So it's a way to actually tell whether the state is entangled or not. Stated differently, the state is entangled if the so-called Schmidt rank is greater than 1. And there's another important property of the Schmidt decomposition, which is also related to the properties of the density matrices and their trace operations and the entropies. And this is something which we will come back to when we look at the example in the exercise which we discussed last week. So just a quick reminder, I hope you can forgive me for being a little bit slow and repeating things, but there are some elements here which actually are useful to just keep in mind. So one of the things which we discussed last week, and I just remind you of the derivations of that, was the Shannon information entropy, which is given in terms of the probabilities. And then we want to make a quantum mechanical equivalent. And as we demonstrated last week, the system which we are going to, or the kind of equations which we are going to look at as a measure of entanglement, is the so-called von Neumann entropy. So this entropy, just to remind you quickly of what we said last week, the entropy is a measure of the impossibilities or the possibilities of being in a specific state. So if you know that you are exactly in a given state, then we know that the probability of being in that state is equal to 1. And then the entropy is exactly equal to 0. So the entropy measures or gives you a measure of unlikelihood. So if the state is well determined, we know that we are exactly in that state, then the entropy is exactly equal to 0, because the probability of being in that state is exactly equal to 1 if we know that. We know we are in that specific state. If we have a mix of states, then as we saw last week from the binary system, then the entropy will be different from 0. So the higher the entropy, the more mixed in a certain sense is a system, or the less certain you are about in which state the system is in. Now, what we did last week was actually to derive the von Neumann entropy, where we wanted to use this probabilistic interpretation, and we found that we could rewrite it in terms of the density matrix. And remember now that the density matrix contains in terms of its spectral decomposition, is given by the probabilities for being in a state times the projection operator of that specific state. So this gives us a way to make a quantum mechanical analog for a measure of entanglement. So if we now are in a pure state, so if you go back to the Bell state which we had, this Bell state here, this is a pure state because it's welded, even if it's entangled, because we know that we are explicitly in this state. So if you prepare the system, you know that it's a superposition of these two states. There is, however, an uncertainty in the subsystems. So if you look at this state here, the 2-qubit state is well determined, and we call this a pure state. Its probability is equal to 1. That means that the entropy is equal to 0. However, if I now want to trace out one of the subsystems, then I may not know whether the system A is in qubit 0 or qubit 1. So the quantity which we will be looking at now is the density matrix for the subsystem A or subsystem B. So if you look at this equation here, the 2-qubit state is well determined. It has a well-determined probability. We know exactly in which state the system is in, and that has probability 1. If I now were to square this and calculate the quantum mechanical probability, I would have 1/2 plus 1/2, which gives me 1. And that gives me an entropy which is exactly equal to 0. And that's a state which is well determined. So keep in mind that when we look at entropy, we are using that as a way to determine the likelihood of being in a specific state. If I, however, look at the subsystems, when I start with this state, this Bell state, I don't know in which state qubit A is in, whether it's in 0 or 1. So what we are going to do now is to calculate the specific definitions. We are going to calculate the density matrix of subsystem A and subsystem B. So in a sense, this is a continuation also of the qubit example, which we had in the second week, where we looked at us setting up the Hamiltonian system. So I wanted to repeat this a little bit because it takes us, you need some rethinking to see the wood for the trees. So what we had in that specific exercise, which we also extended last week to the calculation of the eigenvalues and eigenstates, and also the calculation of the density matrix for one of the specific states. And then with that density matrix for the 2-qubit system, we are now going to trace out the density matrix for one of the subsystems. So the states, the computational basis states we have are these specific states here, which we discussed last week. And one of the things which we assumed is that these subsystems which we have, or these specific states, the computational basis states, they are eigenstates of the non-interacting Hamiltonian. That means that we have a set of eigenstates which we can use to expand the interacting wave function in terms of. So what we then did was to add an interaction piece, which gives me some non-diagonal elements because we have a tensor product of two poly X matrices. And then we have a diagonal elements, which are given by the tensor product of two poly Z matrices. And if I do that, we end up with a Hamiltonian which looks like this. And then we can obviously play around with the constants here. So HC is just, in this specific case, HC and HX are just constants. And if we now look at the lowest eigenvalue, So you could diagonalize this matrix, which then gives you a 4x4 matrix and 4 eigenpairs. Then you have a ground state, psi0, which is, as you can see here, is a linear combination of these basis states. So when you diagonalize, you get a linear combination where these coefficients alpha 0, 0, alpha 1, 0, alpha 0, 1, and alpha 1, 1, they are the components of the eigenvectors which we get when we diagonalize. And then we have the computational basis, which is defined as the eigenbasis of this H0 part of the Hamiltonian, which is a known part. This is a very common way of dealing with quantum mechanical many-body systems. Then you can then define this density matrix for the ground state, which is rho 0, which is simply now the outer product of these states, this linear combination of states. So what we can do next, when we have this, is to define the density matrix for the given subsystems. The density matrix for the given subsystems are going to be given by the trace, where we trace out one of them, operating on the full density matrix for the 2-qubit states. So remember now that we know exactly the linear combination of the ground state. So when we diagonalize, we have these coefficients. So this ground state which we have is actually a pure state. So we know the system is in that linear combination, period. If we were to deal with the Bell states, we would have another example of a pure state, a well-defined state. However, as you can see here, when you look at this linear combination of these 4 computational basis states, we don't know in which state the qubit in subsystem A or subsystem B is in. So that's why we're interested in defining these quantities. And these are the quantities which we are going to look at in a little bit more detail. And the thing which I wanted to bring up as a parallel is something which in statistics is called for the marginal distribution. So after the break, we are going to look at how we can compute this trace or the density matrix for one of the subsystems. And that will give us a measure of the entanglement in the system, in the sense that we are going to measure the uncertainty or the loss of the pure definition of which state qubit this qubits of system A or B are in. So let me just, before we take a small break, let me remind you of what these quantities mean in terms of the marginal density from statistics. And then after the break, we are going to look at how we can calculate this for that specific state. So in statistics, suppose now that we have a probability distribution which depends on 2 variables, x1 and x2. It doesn't need to be the product of 2 individual probabilities, if we are assuming that x1 and x2 are independent and identically distributed stochastic events. Now, I can define something which is called the marginal probability. And that means that I can calculate the probability of just x1. And if this is a continuous probability with the continuous variables, we would have an integral over x2 here defined over the domain of events for the stochastic variable x2, but where we now integrate out x2. So that means that we get just a probability of being in x1. This could be a position, it could be something else. Similarly, if we have a discrete probability, then this P of x1 would then simply be given by a sum over x2 for all these individual stochastic events which we can have. So this is a definition of the marginal probability. So what we are going to do now is actually to trace out one of the variables, because we are going to have a density matrix, which could be given by the ground state of the system. So this is a psi0, the exact state of the system, which then is a outer product of the linear combination of these computational basis states, which make up the state psi0. So this is given by some coefficient, and then I have 0, 0, and then I have an alpha 0, 1, 0, 1, plus an alpha 1, 0. These are just the coefficients you get when you diagonalize that matrix. And then I have an alpha 1, 1 of the state 1, 1. And just remember now that these ij's here, they are just simply the tensor products of the two qubits in the different subsystems. So what I'm interested in now is the subsystem. So I'm going to, in analogy with the marginal probability, I'm going to trace out one of the variables, as we did with the marginal probabilities, where we either integrated away or summed away one of the variables, so that we're just left with a probability in terms of one of them. So what we want now, since the density matrix is actually given by an outer product of the orthogonal basis states times a probability, and that's why the density matrix with the spectral decomposition is so interesting, is something which now allows us to actually introduce this definition of the entanglement and whether we have a pure state or not. Yeah, I see that I should actually have written this out in terms of, I'm sorry for that, there's a comment in the chat here. So sometimes my letter P's are not the best one, but this should be an uppercase letter P. And then this one is a lowercase letter. So these are not the same. So these are two different probabilities. Yeah, sorry for my handwriting here. So what we are going to do after the break is actually to look at how we can now trace out the density matrix, which then allows us to find the spectral decomposition of one of the subsystems. And based on that, we can tell whether we are in a pure state, whether qubit the qubit in system A is in state 0, 1, or if it is in a combination or linear combination of the two possibilities. So let's take a small break. So in this session, we are going to say a little bit more about the calculation of the traces and the density matrices for the subsystems, and how we can link that with the calculation for the simple system, which we discussed before the break, and then how we can extract information about the entanglement of the system. So if we now switch back to the whiteboard, what we are going to do now is to set up the equations for how we can calculate the density matrix for one of the subsystems. And this is, as we discussed before the break, parallel to the calculation of the marginal probabilities, which some of you may have encountered in different statistics courses. And the reason for why we keep this kind of parallel is that the density matrix itself, in its spectral decomposition, is given by the probability of the specific states times the projection for that specific state, where the states which we are summing over are given by a given orthogonal and normalized basis. So let's now look at how we can calculate these quantities here. And in doing that, we are going to switch over to the whiteboard. And after that, we are going to look at definitions of gates and how we can set this up with a software which is called Qiskit. And you should feel free also to follow the textbook by Robert Hunt in chapters 2 and 3, where you can see how you can build up your own code without using a library like Qiskit. But let's now go through these technicalities which I promised. So the overarching picture which I want you to keep is this parallel with probabilities. And we have the possibility now to define a density matrix, and this density matrix is defined for a specific state. So we could define a similar density matrix for one of the other states of this 4x4 matrix. But this is what it looks like for the lowest lying state, which we label with a psi 0. And this psi 0, when we diagonalize, is simply now just a linear combination of these computational basis states, which we defined, which are the tensor products of two individual qubits, one in system A and one in system B. So what we could do, instead of taking this long combination of states, we could just take one of the Bell states. So let's do the calculation of the Bell states. And one of the Bell states which we can pick is, I just picked this one because that was the first one on my list. There's nothing more than that. So we defined a state phi plus for the two subsystems A and B, which was defined as a linear combination. So we have a factor of 1 over square root of 2, which when we square it gives a factor of a half. So this is a probability of a half of being in this state. So we have a tensor product of the, no, this is not A, this is subsystem B, and plus 1 of A and subsystem B. So let's use this as an example. Now we said that before the break that this state is well defined. We know exactly what's the specific probability for being in one of the computational basis states. So we would typically rewrite this as a 1 over square root of 2, and then we have 0, 0 plus 1, 1. This is the more compact notation which we end up using. So if I think back to this Schmidt decomposition, which I discussed before the break, this is a system which has a rank d equal to 2. We have two states, 0, 0, 1, 1. And we have two singular values or eigenvalues for this system, which are the probabilities, which are just 1 over square root of 2. And if I square them, I get the probabilities. And the sum of these two, lambda 1 squared plus lambda 2 squared, is equal to 1. Now, what we are going to define is a density matrix for the 2-qubit system, which is simply given now by the outer product of this specific Bell state of AB. And if I do that, I'm going to get a matrix which looks as follows. So if you do the algebra here, you simply need to take the outer product of 1. We are just now getting squaring this one. So we would have a 0, 0 with 0, 0 plus 0, 0 with 1, 1. And you see now why I picked the Bell state instead of the linear combination of the 4 computational basis states from the diagonalization, simply because then I would have to deal with many more states here. So this is pretty straightforward to set up these outer products. So I would have 0, 0 plus the final one, which would be the outer product of this specific state here. And if I put everything together, what I'm going to get now is a density matrix, which looks like this. So I have 1, 0, 0, 1, and then there would be 0, 0, 0, 0, and then again, all zeros, and then I have 1, 0, 0, 1. So if I do the algebra correctly, this is what we should get. So let's see now, there's a question in the chat here. yeah, in this case, lambda 1, oh, thanks. I have many eagle eyes here. Thanks, guys. So this should be lambda 2 here. Thanks. That's one of these funny things when you teach. I mean, you have the notes in front of you, and they say lambda 1 is equal to lambda 2, but you write lambda 1 is equal to lambda 1. We are humans, fortunately. So let's now look at the tracing out of the subsystems. So when we are going to look at the trace of the specific subsystem, what we want to do now is to take the trace of the subsystem B, and this is going to correspond to what we call the marginal probability. So I'm going to take this trace over B of that specific system. And if I now look at the qubit 0 and qubit 1 of system A, so we want to trace out, let me give you some of these intermediate steps. So we want to trace out qubit 0 and 1 of subsystem A. And this is something which we are going to define by the following operation. So we are going to define an intermediate step here. So we have the identity of a system A, and then I'm taking the tensor product with a system B. So this is a given state in system B. And in our case, this becomes equal, since this is now setting up as a tensor product. And we know that this one is just 1, 0, 0, 1. And if I'm now taking out a specific qubit, 1 or 0, then what I would get then, if I'm looking at qubit 0, then this is going to be equal to a 4x2 matrix, which is 1, 0, 0, 1, 0, 0, and 0. I can do the similar thing for qubit 1. So if I take qubit 1, and now I'm going to trace out qubit 0, and then I will repeat the same with qubit 1. So for qubit 0, I'm now going to calculate this matrix product. So I have 1, 1, 0, 0, and then 0, 1, 0, 0. And then it's multiplied with the density matrix. So I have 1, 0, 0, 0. So I'm tracing out the subsystem B, and then I have to multiply this with 1, 0, 0, 1, 0, 0, 0, 0. And when I multiply this, we have a 2x4 matrix times a 4x4 times a 4x2. So that gives us a 2x2 matrix. And that gives us 1, 0, 0, 0. So that's what I've been tracing out. So I've been tracing out qubit 0 for subsystem A. And then I can repeat the same for qubit 1. And it shouldn't come as a surprise that you then get just 0, 0, 0, 1. So if you go back to this outer product here, that was simply given. And this is just for one of the qubit system, 1, 0, 0. And similarly, this is the same as 1, 1. So I'm now just tracing this out. The thing which I see now is the following. So this is now my density matrix. I've been tracing out the system B. So I have the density matrix for subsystem A, where I now traced out subsystem B of my rho, which is composed of system A and B. And we just use the letter rho for that one. And what we see now, if we add these two together, what we would have then, when I do the algebra, because I have a factor of a half in front of the probabilities, so the And that means that I'm getting 1/2 times the identity matrix. So if I take the trace, which should be always equal to 1 of the subsystem A, if I do that, then you see now if I take the trace of this matrix, I have 1 plus 1 divided by 1/2. So I'm just getting 1/2 plus 1/2, which is equal to 1. But there is an important thing which now is going to allow us to define whether we have a pure state or not. If I take the square of this quantity, what you will see then, if I take the square of the trace, I have a factor of 1/2. So that gives me 1 divided by 4. And then I have the unit matrix squared, which is just the unit matrix again. So I get a factor of 2. But what I see then is that this is equal to a factor of 1/2. So this is smaller than 1. And we normally define that as a mixed state. So if I have the trace, so these are just measures of mixed states and pure states. If the trace is equal to 1, then I call this for a pure state when this quantity is squared. So these are definitions which we now use in connection with entanglement. Another thing you can show, and I leave that as an exercise to you, is to show that this rho of B is equal to, in this system, to rho of A, which is just 1/2 times the identity matrix. Another thing you should pay attention to here is that this composed system, rho of AB, is not the same when you now take the tensor product of the two ones. So I cannot write that as a product state of two individual subsystems. So this is also pretty easy to show. So what we say now is that the joint state of two qubits, whether that is entangled or not, is a pure state. It is known exactly. However, when we now look at the individual qubits of, for example, this entangled Bell state, and we look at the individual qubits of either subsystem A and subsystem B, what we find then is that we cannot disentangle whether the qubit is in state 0 or 1 with certainty 1. That means that this subsystem represents a mixed state. So we don't have enough information to say with certainty that the probability for being in 0 and 1 is exactly 1. So we call this for a mixed state. So the algebra which we did was simply just a write-out of the tracing out of that specific subsystem. And that gives us the density matrix of a subsystem based on the density matrix for the total system. So let's now summarize this. So the joint state of two qubits, which we now looked at in terms of this Bell state, but it could have been the eigenstate of that system which we have been looking at. This is irrespective of whether it is entangled or not. Is a pure state because we have defined it. So it's a well-defined state. So we say then in more daily words, it is known exactly. And in our case, we chose this Bell state of subsystem A and B, which was simply given by this linear combination with a probability of 1/2 when we square it of the substates 0, 0 plus the substates 1, 1 in their respective subsystems A and B. And where we now have suppressed the tensor products. So when you look at individual qubits, so let's add this statement, however, when we now look at individual qubits, what we see then is that for this entangled Bell state, for the state phi plus, or any state, any such entangled state, keep that in mind. So the many-body state is an entangled state. We find that they're mixed by this definition which we have set up. That means that we do not have a full certainty or full knowledge. The full knowledge of their states. And we call this for a mixed state. On the other hand, if we had found that the squared trace and the squared density matrix and the trace of it had been equal to 1, then we would say that this is a pure state. But in our specific case, we don't know whether subsystem A is in state 0 or state 1. So this makes a very important kind of measure for the level of entanglement. What we will see later is how we can use these states to make quantum operations in terms of specific gates. How we can use this feature of entanglement in order to actually try to figure out whether we can set up specific gates, which we will discuss now, in terms of us being able to manipulate such quantum mechanical systems. So one of the things which I wanted to go back to now is the example which we had for this 2-qubit system, and try to understand a little bit more about how this entanglement arises and why this density matrix now can give rise to states which cannot be defined properly. So that means that we would have a state for the subsystem where we cannot say exactly that the qubit is in state 0 or state 1. So let's go back a little bit and just look at the Hamiltonian matrix. So what we are going to do now is to multiply this matrix elements with a constant lambda, which we let go from 0 to 1. So that means that if we multiply this expression with a constant lambda, then if lambda is equal to 0, then our Hamiltonian will just contain this known part. And if you look at the known part, with this constant being 0, then we know that the lowest lying state should be, if this E00 is the lowest lying energy, then this state should be in state 00. This is not an entangled state, and we know exactly that qubit 0 or subsystem A is in state 0 and subsystem B is in state 0. When we switch on these interaction matrix elements, we are going to get a linear combination of states, as you will see here. And when we get this linear combination of states, then the state will be in a superposition of, so the 2-qubit state will be entangled, and but it will be exactly defined. We know that this is given by this combination. However, subsystem A may be in state 0 or state 1, or linear combination of actually these possibilities. So what we will do now is just to trace out these density matrices and obtain the density matrix for the subsystems. And then we are going to calculate the trace of the subsystems, just to see whether we can have an entropy which is equal to 0. That means we have a pure state, it's well defined. And clearly when we have an interaction strength which is 0, then we know exactly where we are, and the states are well defined, and we should get 0 entropy. So let's see in this code here how we can actually perform that. So I'm setting up a set of values for this constant lambda from 0 to 1, and I'm setting up 40 values. So what I'm doing now is simply to start with a system which has no interaction, and then to a system which, when lambda is equal to 1, which we will simply call the fully interacting system, because then we have the interactions in full glory. So I have fixed these parameters so that I will actually get this kind of level crossing we discussed. So here I have the polymatrix X, polymatrix C, the tensor product of sigma X, and sigma C. These are just the non-interacting cases, and I tune these variables so that I can actually see this avoided level crossing. And here I'm just running for these different parameters, lambda, and then I diagonalize. I sort the eigenvalues. I set up the density matrix, the full density matrix, which is then just given by the outer product of the different eigenvectors. And now I'm just looking at the lowest lying one. And you see that this is given by 0, 0 here. And these are the eigenvector for the lowest lying state. I calculate the density matrix. And now I'm doing the projection on the substates. So my diagonal matrix is just 1, 1, as is known. I'm looking at the qubit 1 and qubit 0, no, qubit 0 and qubit 1. I'm calculating the projection as a tensor product between the qubit 0 and the identity matrix. And I set up this projection, calculate the density matrix, do the projection transposed. And then finally, I add the two quantities and I have my density matrix for the subsystem. And then with the density matrix, I now calculate the entropy. And if you look at my entropy here, one of the things we see now is that when this interaction strength is 0, then we have essentially the state 0, 0, 0, 1, 1, 0, and 1, 1. Then as I switch on the interaction, I'm getting components of the wave function, which now have an admixture of the other states. Now let me just see here. There's a question here. Now the alphas, or the sign here means matrix multiplication. So in Python, you can write this as a pointed dot, or you can write it in terms of this symbol, the at symbol. And this now is a new way of actually defining a matrix times a matrix. So previously you would have the dot operation, but then in later version it has been replaced. You can still use that one. I'm not happy with any of these notations. So that's just a personal bias. And then there was another question here as well. Oh yeah, okay. So this is just a matrix multiplication. Okay. Let me just do that one. And when I look at the results then, when I now calculate the entropy for subsystem A, you see now that when the interaction strength is 0, then what happens is that I have a well-defined state, which means that the lowest lying state, which I've picked, is in a subsystem A has qubit 0 and subsystem B has qubit 1. So everything is well determined. But then when I start adding these other components, I get an admixture. And then I get a sudden rise due to the change of states here. So that means that I'm now changing the quality of the eigenstate. So here up till here, it is dominated by the state 0, 0. But then what happens here is that this state, the green one, is the one which takes over. So it means that for high excited state, there is another state which now becomes dominant. And this is reflected also in a change in the strength of the occupation of the different subsystems. So what you see here, this entropy here, is just our degree of uncertainty. And when it increases, it means that we cannot tell with certainty that the qubit in system A is in state 0 or state 1. And the final state is actually not dominated only by one, but it actually has a linear combination of many of these states here. And so this simply measures the degree of, and it's a measure for the degree of entanglement for the subsystem. And you should read this as our lack of ability to determine precisely in which state you are. So this exercise, which we had from last week, is something which I would recommend taking a look at again, because you will see it popping up in the first project. Now, for the second project, one of the possibilities is actually to use systems like these to design quantum gates and quantum operations. And you will see that when we come then to actually designing gates, being able to exploit states which are entangled or subsystems which are entangled becomes very important. This is something we will discuss later. So this feature here, as it stands here, we have used it as a measure of uncertainty or lack of capability to say in which state the subsystem A or subsystem B is in. But later we will actually use this feature to set up quantum operations like swap gates or C0 gates. We will come back to this. So I'm just anticipating why this is a very interesting feature. Now, one of the things which I wanted to do now is to switch to some specific gates. So if you scroll down in the notes here, and this is the kind of things which we will need for the next session, which will be a hands-on session, where we will go through the setup of Qiskit, how we can set up gates, etc. These are things which I want you to take a look at till next time. And now I'm simply going to set up some of these gates and discuss what they look like and mathematically what kind of operations we're actually dealing with. So mathematically, we are going to express given physical processes in terms of specific matrices. And there are some gates which are widely used in the literature. And some of these are then represented by the application of specific matrices times a state. And some of the famous gates or matrices, as we see them, are given by the Pauli matrices. We have the identity matrix or the unit matrix, and then we have the famous Pauli matrices, which are now rewrite as X, Y, and Z here. So these gates form a basis for the SU2 algebra. You can exponentiate the gates. You can look at rotations. So these are quantities which we will be discussing in more details in the coming lectures. But I wanted just to give you a kind of bird's view on some of the more famous gates and how they can be rewritten in terms of matrices. But keep in mind that these operations all represent specific physical processes. Before I do that, I just wanted very quickly, besides this material which you see here, I wanted to give you a quick introduction to Qiskit. The reason why I do that is because I'm going to give you a kind of homework to actually look at these notes, because they contain also exercises which we will look at next time. So Qiskit is a library which has been developed by IBM, and in a way it defines their interface software with the quantum computers which IBM have developed. And it's actually a library which has advanced a lot. And the library here, the way you would install it, if you haven't done that, is just to install Qiskit by these instructions here. You can set up, define the number of qubits, the number of classical bits. We are coming back to these things. You can set up what's called a quantum register. These are quantities which we will discuss. You can set up a quantum circuit, and then you can draw it. So what's often done, and as we will see now repeatedly, in the weeks to come is that we will set up quantum mechanical operations in terms of circuits. So if you look at like this operation here, you can now draw a circuit. Actually, here there is nothing to draw because we are not performing any operations. But you will have something like this, where you now have a X gate or Pauli gate, which is now acting on a specific system. You can then select a qubit you want to make a measurement on. So that means that you have a Pauli gate here, a Pauli X gate, and then you perform a measurement. You can execute it. There is a backend here, which is normally used. And then you can perform the operation on it. And you see that this collapses to a qubit 0. And you're going to perform this a series of times. You can create a 2-qubit Bell state. And the way you would set this up now is to have a so-called Hadamard gate. And then you have a new Hadamard gate. And then you perform a measurement. You project out qubit 0 or qubit 1. And these are all things which we will come back to. So I'm taking the liberty of giving you a homework for next time to get a little bit familiar with the library. And we will be discussing the library and how to use that next time. And there are exercises for next week, which Karen has developed. And they mesh well with what we are going to do in the first project. And we are going to play around with these Bell states next time. But what I wanted to do now is just to discuss some of these gates, which we are setting up in terms of different matrices and how they link with classical gates or classical operations, which some of you may have encountered before. So let's go back to the whiteboard and just end today by looking at some of these classical gates and their quantum equivalents. So let's take a look at some of the classical ones. And in computer science, there are actually proofs that you can build and perform all kinds of operations with a set of these classical gates. So we're going to define these as classical gates, and we're also going to look at what we will call as a circuit. So a famous gate, which many of you probably are very familiar with, is normally called the NOT gate. So this is a state. We have a state X, and we feed that in, and we normally look at the potential differences. So this is often implemented via transistors. So if the potential difference is below a certain value, you would output 0 or you output 1. So if you look at the truth table here, you have X and Y, and the NOT gate is so that if I feed in a bit 0, then this results in bit 1. If I feed in bit 1, this gives me bit 0. There is another gate, which is also very famous, which many of you have probably encountered. This is the XOR gate. You have the OR gate, you have the AND gate, you have the NAND gate, but you have actually a combination of some of these gates with which you can perform essentially all types of operations. So we have an input X, a bit X, and a bit Y, and that produces a bit Z. Now, you should notice one thing is that the NOT gate is what we call reversible. So that means that if I know the value of Y, I know what X was. If you look at the XOR gate, this is something which, so the NOT gate has a quantum mechanical equivalent because it is reversible. So keep in mind that everything we end up doing is given in terms of unitary transformations. So this is an irreversible gate. And the reason for that, if you now set up the truth table, is that you have an X, Y, and Z, and the XOR gate is set up so we have 0, 0, and that gives us 0. If I have 0, 1, it gives me 1. If I have 1, 0, it gives me 1. And if I have 1, 1, it gives me 0. So the reason why we say it's not reversible is that you see that if you have z equal to 0, you don't know whether x and y were 1 and 1 or 0 and 0. And similarly, if you have z equal to 1, you don't know whether bit 0, x or bit y were either 1 or 0. So we would typically call this for an irreversible gate. There is another famous classical gate, which I'm setting up here, which is called the NAND gate. This is also an example of a irreversible gate. So it means that there is no quantum mechanical analog of that specific gate. So we have an output z, so we have x, y, z here. And this specific gate, we are feeding in 0 and 0, we get out 1, we feed in 0, 1, we get 1, 1, 0, we get 1. And finally, if we feed in 1, 1, we're getting 0. And this is also a case, unless for 0, where we know that the input has to be 1, 1. If we look at the ones which we get as outputs, we cannot trace back and say whether that specific gate or that specific state x and y had a value which we can define. So when we look at quantum computing and gates, what we need then, when we now switch over here, so look at quantum computing and gates, then we have that the inputs and the outputs they are in principle n qubit states. And you saw that we had this case with the 2-qubit system. And then we could set up a 2-qubit state, which would be a vector of length 4. When we then operate on that one, we would typically operate with a, let's say, a projection matrix, which would be a 4x4 matrix, etc., etc. And if we now, just as an example here, we know that the 2-qubit state, 2-qubit, that could be equal to 0 of A, and then the tensor product of 1 and B, just to give you an example. We have a orthogonal basis set. We are going to define now different types of gates. We are going to define 1-qubit gates. We are going to look at some famous 2-qubit gates. And also higher qubit gates. So we can define 3-qubit gates, etc., etc. So we can continue like this. So there's going to be an initial state. And this initial state is a state which we label with a vector psi. And then there is going to be an output state of these operations. These operations can be a measurement where the state collapses to a specific state. So this is our output state. And in principle, what we are going to have now is a series. So this G, which you see here, can be a series of operations on that state. And these are unitary transformations. So keep in mind that we want to apply quantum mechanics, obviously, and that means that we have to have operations which are unitary transformations. And unitarity ensures also reversibility. So if we now look at the 1-qubit gates, there are some famous ones, and these are the Pauli matrices. So if we jump into that topic immediately before we stop this week. And as I said, I would like you to look at this exercise material and how to implement Qiskit, so that when we meet next Wednesday, we are going to have a plain hands-on session. Then my hope is that you looked at some of these exercises. Feel free also to look at the project description, because that is something which we will also discuss during the hands-on session. So that means that there will be no type of lecture like now, next Wednesday, but we will start looking at the specific elements which we need which we're going to need in the project. So if we take the 1 qubit gates, you could think of an initial state, which is a linear combination. So we could make an initial state, which is psi, and that is a linear combination of alpha 0 of 0 plus an alpha 1 of 1. And then we can have an output state, and this is roughly where we will stop today. So let's just write it out in terms of an operation here. So we have an output state, which now could be an alpha 0 prime times this state, plus an alpha 1 prime times the computational basis state here. Then what we will be doing then essentially is to define an operation where we have a matrix. This is the way we perform the transformation. So this has elements G00, G01, G10, and G11. And we are going to define this to be a unitary transformation. So that means that this quantity here, when I calculate this one, then this has to give us the unit matrix. And then that means that when I set up the state, and this is the last thing which we will be doing today, is that the new state will be given by this unitary transformation of the original state. And that will give us, since we're just dealing with 1 qubit, we will have an alpha 0 and an alpha 1 prime, which then are given by the matrix elements of this unitary transformation of G10, of G11, acting on this state alpha 0 and alpha 1. That is our initial state. And what we will do next time, I'm also going to make a video, which is a continuation of what we discussed today, so you can take a look at some of these specific gates. We are going to practice with 1 qubit and 2 qubit gates. So there's a question in the chat here. Yeah, I can do that after the lecture here. So let us stop here today, and then we next week we are going to do this hands-on session and prepare, set the ground for the project as well. But now I'm going to stop the recording here.